Today we will look at the power consumption in digital circuits, which can be divided into two types. First, dynamic power, which is the power associated with ones and zero transitions. And second is static power, which is basically the power that mainly depends on transfer technology and temperature. In this video, we will look at one of the dominant sources of dynamic power and derive a mathematical expression for it. Consider a basic CMOS circuit with a PMOS on the top and a NMOS on the bottom, as shown in this diagram. On the bottom it's connected to the ground, and at the top there is voltage supply VDD. The input connects both the transistor gates. Also consider that there is a load capacitance attached on the output. Now this circuit functions as a NOT gate. That is, when the input transitions from 1 to 0, the output transitions from 0 to 1. Similarly, when the input transitions from 0 to 1, the output transitions from 1 to 0. The dynamic power is the total amount of power used in charging and discharging of this capacitor, as the stream of ones and zeros constantly come as an input to this circuit. So let us consider the first case, where the input goes from 1 to 0 and the output as a result goes from 0 to 1. In this case, the voltage supply leads to charging of the capacitor. Let us derive how much energy is delivered from the power supply to charge this capacitor. Consider the charge on the capacitor, CL, multiplied by the voltage across the capacitor. Since the charge is changing as a function of time, and even the voltage across the capacitor is changing as a function of time, we can find the rate of change of the charge with respect to time as the load capacitance CL, which is constant, multiplied by dV by dt, which is the change in voltage with respect to time. The charge with respect to time is nothing but the current across the capacitor. The energy per transition, ET, can be written as the power, which is the current that you are delivering from the power supply, multiplied by the voltage. This gives you the power, and this we have to sum up over some interval of time. So let's say we integrate this from some interval of time. Here VDD is constant, so we can take it out of the integral, and ICL, as we just derived, is CL dV by dt as a result. Load capacitance is also constant, so we can take it out of the integral. So we are left with CL VDD and then this integral dV. The integral of dV is summation of the final voltage. So the energy used is CL VDD squared. So this is the energy for the transition going from 1 to 0. Similarly, we can also derive the energy that the capacitor is storing inside of it. So the energy stored in the capacitor, so this is nothing but the integral of the current through the capacitor, which we know is CL dV by dt. But notice the difference. Unlike the power supply, which is fixed, the voltage across the capacitor is changing. So the voltage here is actually changing, and we give it a variable V. And then we essentially want to sum it up over the interval of time 0 to infinity. Of course, this can be simplified as you can bring the CL outside the integral term. So we are left with V dV 0 to infinity. This infinity is nothing but V dt, because that's the final voltage that you arrive at. So the energy can be written as half the load capacitance V dd square. What is interesting is that earlier we saw that the total energy delivered from the power supply was capacitance times V dd square, whereas the energy stored in the capacitor was only half of the capacitance times V dd square. So where did the other half go? We only store half the energy and we dissipate half of it. Now we can go and derive the dynamic power. The dynamic power can be derived from the energy that you spend in one of these transitions. So the power for the transition, let's say we're going from 1 to 0 on the input, that is the energy for this transition times the frequency of these transitions. So in a stream of ones and zeros, you may sometimes transitions more from 1 to 0 than 0 to 1. As a result, you don't really know what is the probability of these transitions. So let's assume the probability of these transitions is alpha, which is between 0 and 1. And then you can multiply this by f clock. So as we already know, energy for this transition is nothing but CL VDD square. We still have this alpha times f clock. So we can actually write the power for these transitions, or dynamic power in general, as C dyne, or dynamic capacitance, times VDD square times f clock. The C dyne is nothing but a multiplication of the load capacitance and the probability of transitions alpha. Thank you.